Hello everyone, I am Yongxian Chen from National Zhongzhen University, Taiwan. It is my honor to present my paper titled Uniformity Correction of Large Area XY Strip Detector with Multi-Leaf Collimator. Here is the outline of my presentation. Abstract. In this study, we use a medical linear accelerator (LINAC) and a multi-leaf collimator (MLC) slit to generate a strip-shaped radiation source. The detector's results in both directions were recorded after the MLC slit scan, generating a lookup table (AUT) for error correction. We conducted two tests. Table test to verify the accuracy of the AUT. Daily QA test to evaluate the effect of AUT correction using a 10 by 10 cm square field with 7 different beam types. Results showed that our AUT-based method is easy to implement and effectively reduces detectors errors to approximately 1% for a 28 by 30 cm area. Background. In radiation therapy, daily quality assurance requires both accuracy and efficiency. Compared to pixel-type detectors, strip-type detectors have some advantages. For the same detection area, an AXY strip detector achieves high resolution with fewer readout channels by utilizing an N plus N multi-channel design instead of an N-square pixel type array. This design allows for faster and more efficient QA testing. Figure 1 shows schematic diagrams of pixel and strip type detectors. Instrument and method. In this section, I will introduce the X-ray strip detector and the generation of the LUT. X-ray strip detector. The detector consists of three main layers, a high voltage plate, and a spacing layer, and a strip detector layer. The circuit is embedded within the PCB, allowing both X and Y directions to share a single sensing layer. It features 127 strips in both the X and Y directions, with a sensing pitch of 2.72 mm and a total sensing area of 345 square millimeters. Generation of LUT. To generate the LUT, we use a LINAC with the following parameters. A 2 by 30 cm slit was created using the MLC. It started at x equals negative 16 cm and moved in 2 cm steps until reaching positive 16 cm. During scanning, the X channel results follow a Gaussian distribution. The Y channel result exhibited a flat-top waveform covering channel, as shown in Figure 3. After completing acceleration scan, the LINAC was rotated 90 degrees and the same process was repeated for the Y direction. The entire process took approximately 36 minutes. The first and last slit positions were discarded due to incomplete slit coverage, leaving a 28 by 30 cm area with 1530 response points. These ADC values were extracted for analysis, where I represents the slit position and J denotes the channel number. The center value serves as normalization reference, yielding the normalized LUT as in equation 1. The LUT in Y direction is obtained in a similar way. Results. Results of this study, which are divided into following three sections. LUT. LUT obtained from the slit experiment are shown in Figure 4. The center error within the measure range reaches plus or minus 2.7%, and the absolute response difference D reaches up to 15%. Additionally, as shown in Figure 4a, the detector shows non-uniformity with a 3% higher response on the channel before 63. Fluctuations are more pronounced on the left side in B. Table test. The table test aims to demonstrate the stability of LUT method. We obtain multiple tables under the same slit parameters on the same or different days. We selected one table to construct the LUT, which was then applied to correct the other tables, as shown in Table 1. When the LUT was applied to its own reference table, the result was around 1.0 with a standard error of 0, confirming that the method worked as a null test, as shown in Figure 5. When we applied the LUT to other tables, the correction remained within 1.0%, demonstrating that the LUT method is effective and stable in correcting the detector surface response. Daily QA. A routine QA procedure was conducted using 7 different photon and electron beam energies, each delivering a 10 by 10 cm square field. We measure the beam profile using the XY strip detector. For the Y channel, the LUT is constructed by indexing each channel based on the radiation range, as shown in equation 2. Here, n is the total number of elements in the table, and it gives the correction factor CRT. To obtain the corrected value, we divided the actual measure value channel measure by the correction factor, as shown in equation 3. A similar approach is used for the X channel. The central region of the beam profile is extracted and fitted using a quadratic function, as shown in equation 4. To evaluate the fit, we calculate the chi-square score, as shown in equation 5, and normalize it by the degrees of freedom. The results are summarized in the table on the next page. The corrected beam profile is shown in Figure 6, where red dots represent the original data. Blue dots and blue line represent the LUT corrected data and the corresponding fitted curve. Table 2 presents the score before and after beam profile correction, demonstrating the effectiveness of the LUT method. Discussion and conclusion. The current square field correction is straightforward since all channels share the same radiation range. Future clinical applications with complex patterns will require more precise range determination for accurate LUT-based corrections. Cobalt 60, commonly used for calibration, assumes initial field uniformity but corrects for its spherical radiation shape, maintaining a 2.16% maximum deviation at 15 cm. When using a LINAC, analysis of 16 positions confirms the central 20 cm region is flat enough for calibration, making a 6 MV beam with an MLC-defined 2 cm slit a reliable LUT calibration source. Further improvements could include a database averaging multiple response maps to minimize dose fluctuation. Conclusion. This study proposed a method for constructing a lookup table based on the LINAC as the radiation source for surface response of the detector. Through data substitution by position and channel, the uniformity error within a large area of the XY strip detector was reduced from plus or minus 2.7% to below recommended 1%. Additionally, during the QA test, the beam profile became smoother and better follow quadratic fitting, improving the quality of the beam profile QA. Thank you for your attention.